So, welcome back. In our journey in this study of knowledge representation and reasoning, we started by saying that our representations have to be symbolic, and then we built upon that and started looking at logics as a mechanism not only for representation, but also for reasoning essentially. So, when we were looking at reasoning, we were not concerned about meaning at all. Logic does not look at meaning, logic does not look at truth value, it is just a symbol processing machinery, and that works to its advantage, because then we can say that our machinery has these properties and so on. And essentially, if you give us a knowledge base or a set of axioms or a set of premises which are true, our machinery will automatically produce other true statements, even though it is not aware that the statements are true or not. Exactly, it is just aware that the statements exist. So, a logical machinery works only with a collection of statements, and we have shown that for a complete and sound system, those statements would be true statements and only true statements. Then when we move towards representation, we started looking at the choice of predicates and how to represent sentences. We moved towards this idea of having a standardized representation in which we use binary predicates for everything, and we came up with this idea of triples. So, we take up the action from there now, and we want to see as to, with the advent of the World Wide Web, when people want to exchange information across the web, and we want our web to be more meaningful. So, we use the term the semantic web. As you know, semantic refers to meaning. So, now we are saying that we are coming back towards meaning, we want our web to be meaningful. Initially, when the web started evolving, we had HTML pages, or we had this HTML markup language to create pages which other people could see. And it did not know anything about what was being represented. From there, we want to come to a stage where the web is meaningful, in the sense that anyone who looks at it should be able to say what we are talking about essentially. Obviously, meaning is, we have said this earlier, it lies in the mind of the beholder, but what we want now is shared meaning. It is like language, that language is a mechanism which works because the speakers of that language or the users of that language have a common notion of what the words and sentences in that language mean, and in that sense it is meaningful essentially. We want the same to happen to the semantic web. We are now moving towards representation, or we have moved towards representation, and in representation meaning is obviously important, because when we represent something, it is eventually for the consumption of some users who would be concerned with meaning essentially. So, we started this phase of our this thing by looking at how one can meaningfully represent information on the web essentially. The information can be consumed by users or by programs written by users, which may do meaningful things with the information or useful things with the information, if you prefer that. So, we will start this phase with looking at this thing called RDF, Resource Description Framework, which is a data modeling technique which allows us to have a standardized way of representing data on the web essentially. These slides, as you can see, I have taken from S. Bhaskaran, who is an expert programmer and who has been working in the area of semantic web and ontologies quite recently, and these are the areas that we are going to look at now. So, resource description framework or RDF is a language for representing information about resources in the World Wide Web essentially. RDF documents can be stored in various formats. We are not going to be too much concerned with that. Our idea is not to learn RDF here, or as we will see RDFS. Our idea is to get a feel of what is RDF and what is RDFS, and later on what is OWL and what does it allow us to do. So, RDF is basically talking about resources essentially, and it uses various conventions as you can see here: URL, URN, URI and IRI essentially. Let us look at them. Resource identifiers denote resources in the World Wide Web. Resources identifiers have a global scope, which means you can access them from anywhere and they would in some sense mean the same thing. The same resource identifier in different RDF documents, RDF graphs and query result sets on different machines identify the same resource on the World Wide Web. What is the resource? We will see in a moment. A resource may have many resource identifiers, just like a human being may have aliases and multiple names, but a resource identifier should represent only one resource, which is what we try to do when we are talking about humans by putting suffixes like Suresh 29 or Geeta 73 and so on, but now we are moving to a more standardized approach which RDF gives us. So, what are resource identifiers? So, the first one is URL, Uniform Resource Locator, points to a location resource on a computer. So, for example, the IIT Madras website www.iitm.ac.in. A URN or a uniform resource name is a persistent location independent identifier, and the simplest example of that is the ISBN numbers that books have. You can identify a book by its ISBN number essentially. Then we have a uniform resource identifier is either a URL or a URN. This resource locator names are resource identifiers. Then we also have the internationalized resource identifier, which allows multilingual representations. So, as you can see in this example here, we have 3 Wikipedia pages, one is in Sanskrit, one is in Hindi and one is in Tamil essentially. So, all these conventions follow different specifications and different character sets. In practice, IRIs are encoded as URIs, and therefore, where a URI is intended, an IR can be supplied essentially. Now, critical to the use of RDF is the notion of namespaces. Because we want a name to mean something specific, we put names of resources into a namespace, and the namespace in some sense sends the context. It defines the context in which the names are being used essentially. So, a namespace typically has a name which is for example, here this is a namespace for RDF schema. So, this RDF schema is an extension of RDF which has a set of names which can be used to describe or relate resources, and some of those words or names in the namespace of RDF schema are sub property of, we will see this what these mean, subclass of or a class essentially. A class will basically be a category, a property will basically be a relation between 2 elements. We can use short names. So, instead of using this entire name, we can simply say that we just want to say RDFS colon, and that is the way to refer to that particular namespace. So, as you can see here, all these references have been shortened into simply saying that RDFS followed by the name that you are talking about. You can go even further by saying that this is going to be my default namespace, that if I do not specify a location, then this is what I mean. And in this example, what it means is that we have some tutorials for knowledge representation and reasoning course, and the names used in the tutorial are the names that will be referred to if we just give a colon and nothing else. So, as you can see here, there are 3 names Rang, India and Poet, and we are saying that these are names from the namespace that we use in the tutorial essentially. Now, there are many namespaces. We have RDF to start with, RDFS, which is RDF schema, which is an extension of RDF, which allows us to talk about more things. OWL is an even more expressive extension of the same class of languages. So, we have these schemas, RDF syntax, RDF schema, OWL. Then we have XML schema, which evolved after HTML was used. Then people started using XML, which was more expressive and more flexible in terms of what you could say. Then we have the database, the Wikipedia of databases, then and we have this Yago, yet another great ontology. So, whenever we talk about the semantic web, we inevitably talk about ontologies, and we will see what we mean by that. Sometimes we know that a resource exists, but we do not know where it is from which namespace does it come essentially. So, we can use just an underscore like here to say that this is a local name essentially. Blank nodes are local to the RDF graphs and query results essentially. And if different programs were to access it, then it might give you different results. Now, there are various kinds of data models that people talk about, and RDF is just one of them essentially. So, here we have listed a few of them: the entity relationship model, ER model, the relational model, the XML model, the property graph model, and now we are talking about RDF essentially. And RDF, as you will see, is made up of resources, properties and statements. So, this is our domain of interest, so to speak. The domain is modeled using 3 elements. Our domain of interest is RDF, and the domain of RDF is modeled using 3 elements. These are resources and properties and statements. And we have graphs and documents are used for organizing statements, collecting them together and putting them in one place. Now, resources, everything is a resource as far as RDF is concerned. We are talking about things, and everything that we talk about is going to be a resource, and it will have a unique identifier, and everything therefore is an instance of RDF resource, RDFS resource. So, they can be physical or real objects or individual elements. So, for example, something called Rang, which we will see or which we have seen earlier, and YouTube, India and Amir Khusro. You might remember the example that we did towards the end of knowledge representation. This thing, we can have abstract concepts like Sufi or genre. We can have categories or classes like song, artist, studio, and we can have properties. As I said, properties are relations between 2 resources. So, we can say poet, that the poet of this poem is this person, and likewise singer and date. So, as we said, properties are binary relations between resources, and optionally, if you are working with RDFS, we can define what is the domain of the relation and what is the range. So, the domain is the starting point and range is the ending point, if you can think of it as an arrow in a graph. So, domain is a RDFS word and range is also an RDFS word, whereas property is an RDF type, as you can see here. So, for example, when we talk about poet, as I just said, the domain of poet is a song, the range of poet is from a class called poet. Remember that this is an RDFS class, and poet is a relation. So, poets kind of sits here essentially. Likewise, singer is a property which connects an event to a singer, and date is a property which connects an event to a date. So, notice that this poet and these singers are classes. Essentially, it says that the a song which comes from the category song, a specific song which comes from the category song is related to a specific element which comes from the category poet. So, poets will have a class of its own, likewise singers will have its class and so on, and these are defined in RDFS. So, a statement is a triple, that is how we arrived here, that we want everything to be expressed in a standardized compact format, and the triple, for example, that Rang has a poet who is Amir Khusro essentially. As far as the encoding goes, it is simply 3 URIs, Rang is a URI, poet is a URI, and Amir Khusro is a URI. As far as the lexical view goes, there are 3 resources that we are talking about. Remember that the property is also a resource, classes are also resources, and elements are also resources, or individuals are also resources. So, everything is a resource, we said that already. The data view is that we are talking about a resource which has a property which has a value essentially. The logical view is that we are talking about a subject, and there is a predicate which relates the subject to the object, and the logical view would look like this, where you say predicate, that is our standard way of logical representation, predicate subject object. So, for example, poet is a predicate and the 2 arguments are the song or the poem and the poet. As we have already said that a statement is a triple and it can be an edge in a semantic graph. So, we saw this when we were talking about Rang and its associated data. So, here we are specifying a little bit more about that. So, first we are saying that the poet, the type of poet which is an RDF keyword is an RDFS class, that this poet with a capital P is an RDF class, and it is a subclass of another class which is called persons, and singer is a RDFS sub property of artist. So, artist is a property and it can include other kinds of artists. So, for example, a painter or whatever, and singer is a sub property. So, both of them are singer and artist, they connect an artwork to the artist, and singer basically connects songs to singers. So, we have already seen this. Rang poet is Amir Khusro, Rang genre is Sufi, performance title was Rang, and so on. So, the RDF data model, a set of statements form a graph. So, we put together different statements, and because they have shared resources or shared nodes, one end of the statement will connect to one end of another statement essentially. It could be that we are talking about performance 101 and then many things are linked to that, or it could be even a chain of things. So, basically graphs and documents are used to organize triples. Graphs are stored in RDF documents and one unnamed graph per RDF document, and we may have additional named graphs which we can import from elsewhere. So, this is how the data on the web looks like. It's called linked open data, and if you just search for LOD cloud on the web, you will be taken to the site which kind of points to this LOD cloud, linked open data cloud, and then you can see how many collections of such documents are existing on the net and how they are related to each other essentially. So, basically the linked open data is made up of RDF documents which can be graphs, which can have subject predicate object relationships, which are talking about IRIs, and the IRIs point to real things in the domain. So, some element in the domain, for example, Amir Khusro, and so what you see at the bottom in the shaded part is the real world that we are talking about, and what you see on the top is this whole vast network or cloud of documents that is talking about them. Databases are stored in what are called as triple stores. So, they store these triples. Remember, triple is a binary predicate sentence, subject, predicate, object, and so on. And they support a query language called SPARQL, which is an interesting one. So, here S stands for SPARQL itself, P stands for protocol, A stands for AND, R stands for RDF, and QL stands for query language. So, R stands for RDF and S stands for the whole word SPARQL itself, and protocol and so on. So, it's basically a query language, just like SQL. SQL is used to query relational databases. SPARQL is used to query graph databases or triple stores as they are called. And essentially, you can specify graphical patterns that, for example, you can say look for a pattern like this. In the graph database. So, 4 nodes which are connected by this specific pattern and retrieve them essentially. Now, you would recognize this, that if you were talking about the family database that we did earlier, then this represents a uncle or an aunt relation. So, there is an individual here and then the parent of the individual, then the parent of the parent, and then a child of the parent, and the child is different from the first individual's parent essentially. So, we can retrieve such patterns, and if you specify here, for example, if you say that who are all the aunts and uncles of Sushila, then we can just query using this pattern, and SPARQL will give us all this data essentially. Now, there are various triple stores listed here. Allegograph is a well known one, but there are others, Virtuoso, Stardog, and so on essentially. Okay. So, let us take a break here, and we will come and look at some more examples and then see how we can move on to something which is more expressive.